Thanks for coming, and welcome to our MaRS Market Insight Series, Beyond the Solar Module, Optimizing Performance and Maximizing Returns. My name is John Dogtrum, and I'm the Practice Lead for Clean Tech here at MaRS. For those of you who are not familiar with MaRS, we are a not-for-profit working to accelerate the commercialization of new technology. And what we're doing is we're helping to build the innovation economy in Ontario, and we're creating jobs and wealth. At the end of the day, what we want to see are jobs coming from new technology and innovation in our province. There are three other practices similar to how we operate in clean tech here at MaRS. There's a life science group, an IT group, and also a social innovation group. What we do in our advisory services is we help entrepreneurs. And in clean tech, we focus on water, energy, transportation, and advanced materials. And we have a group of advisors, most of whom are volunteers and former seasoned entrepreneurs as well, to really help and provide some advice and assistance to the up-and-comers and the new ventures that come through the door. We provide education programs, we provide market intelligence, and we have links to strategic partners and can make some introductions for people. And as well, the venture capital and angel investment community we have good ties into. So we help people with financing and getting the capital they need to grow their business. The session today was put together by Jessica Briones, who leads our market intelligence team for the clean tech practice, and she actually leads market intelligence for all of the regional innovation centers throughout Ontario in clean tech. And we have those regional innovation centers following us on a webcast today, and they'll have the opportunity to ask questions as well. So the gathering here goes beyond just this room. I have the pleasure of introducing our moderator, JoAnne Butler. JoAnne is the Vice President of Electricity Resources at the Ontario Power Authority. Prior to joining the OPA in 2008, she was with TransAlta, where she was the president for their operations in Mexico. And prior to Mexico, she was TransAlta's general manager for Western operations based out of Calgary. She's also has extensive experience in oil and gas with Amoco in exploration and in engineering and construction in Canada and internationally. And she was also with an executive with the Canadian Chamber of Commerce. So please join me in welcoming JoAnne.
Well, good morning, everyone, and thank you, John, for that very kind introduction. Your resume always sounds more elegant when somebody else reads it, but it was all true. I'm pleased to have the opportunity today to meet some of the MaRS people and to learn more about the MaRS organization. I know it really is a model for its innovation and incubation of innovation and for its sustainability practices. And we at the OPA believe that innovation and sustainability are very much a part of what we do on a day-to-day basis. So there is a lot of synergy between the organizations. I'm very excited to be here today. As John mentioned, as Vice President of Electricity Resources at the OPA, my group still is currently responsible for the design and the implementation of the Ontario's feed-in tariff program, or the FIT program. And we're committed to continuous improvement, continuous feedback on that feed-in tariff program. So today it's very much a win-win for me. I get to hear some great commentary and feedback and stakeholdering from the community, the people that have brought this program to life, and as well assist the MaRS Foundation here with helping out as moderator. So we're lucky to have three experts today who are actively engaged in Ontario's growing solar power industry. So here to talk And I'm going to go back to my seat now because I left my paper over there. We're going to talk about three things today. The state of the market for solar PV balance of systems, best practices for system monitoring, operation, and maintenance, and challenges and potential solutions for Ontario's connection and grid constraints. So our first speaker is Matthew Feinstein, Research Associate with Lux Research's Solar Systems Intelligence Practice. Matt researches solar modules, power electronics, system grid interconnection, and other balance of systems technology. He's also contributed to projects with Lux Research's Smart Grid and Electric Vehicles Intelligence Practice, and the EPA's National Vehicle Fuels Emission Laboratory. So please welcome Matthew Feinstein.
Thank you, and thank you for having me this morning. Good morning to everyone. Personally, when I think outside the module optimizing system performance, I think power electronics. And this is a field that we've analyzed fairly heavily over the last 6 months to a year at Lux. And before I get into it, just a quick sort of overview of Lux Research, who we are, what we do. Our core competency at Lux is technology scouting. And we've got practices in the 12 areas that you see in the third bullet there. Personally, I lead our solar systems intelligence practice. We cover everything from the modules downstream through project finance and development, as well as balance of systems, notably inverters. We're also an international company. I'm based out of Boston. We've also got offices in New York, Singapore, and Amsterdam, and we've recently opened shop in Shanghai. So first, I'll give a sort of quick overview of why talk about inverters at all. Then I'll talk a little bit about our research and analysis in the field. We've done quite a bit of work both on the technical side as well as on the competitive landscape side. So first off, obviously, why talk about this? Inverters are the single highest system cost outside of the module in terms of what makes up the total cost of a solar system. But more importantly, I think is bullet number 2 up here, which is that they're also the big problem in solar systems. The majority of the time, that installers or developers or whoever, holds the burden of O&M has to go out, send a truck out, send a worker out to a solar system to perform maintenance is because of the inverter or the electronics, managing the power in a solar system. And really, ideally, because of that, an installer or whoever does hold that maintenance burden would like to, do things infomercial style. They'd like to set it and forget it. But that's never really going to happen. It hasn't happened in the past because there's always some kind of trade-off with cost and performance, as well as the overall reliability of the system. And also, there's a lot of new startups in the space that have caught the eye of the venture capital realm. We advise a lot of VCs on this. They're often looking for a new investment, a competitor to the incumbents who have been around for many, many years. It's very much a new shiny toy that people are quite interested in. So something else to keep in mind is that there's also these new things called power optimizers. And if you go out to the Courtright trailer outside, you can see one of the SolarEdge DC-DC power optimizers that go on the back of panels. And I'll talk about SolarEdge specifically in a few minutes as well. These, basically perform what's called maximum power point tracking. They find the ideal spot along the IV curve for a solar module in order to extract as much power as possible. They can also possess, safety features like preventing overcurrents and ground faults. And they can be placed sort of at the string level, so they can optimize the power coming out of a string of modules, or most often they're at the module level. They optimize the power from each individual module. And the real important thing to note here is point number 4, which is that a lot of these companies, we know them today as having this, separate box that can go on the back of a module, but most of them are integrating into the junction box. They're starting to, come out with a junction box from one of the, conventional junction box makers like Shoals, powered by Taiga or powered by Amped. This is going to be interesting for reducing costs in terms of integrating components. And obviously, it doesn't have to be thrown on the back of a module now at the site of installation. It just happens at the module factory. So This is the way things are in terms of the competitive landscape for inverters. Most of the companies you see on the left side, well, first of all of the companies you see on the left side are string or central inverter manufacturers. All of the companies that you see on the right are microinverter or module level DC-DC power optimization companies. They're doing something on the module. Companies on the left aren't. They're aggregating power from a string or from an array and then inverting it from DC to AC. The other difference is that most of the companies there on the left were started sometime in the 80s. And most of the companies, if not all of the companies that are solely in the right side of the Venn diagram are pretty new. And this is what I say, or what I mean when I say that they've caught the eye of the venture capital space. Most of these companies are venture-backed and fairly new and upcoming and really vying for small bits of market share. The interesting thing is that there used to really be nobody there in the middle. Power One recently moved into the microinverter space. They added that as a product offering to their string and central inverter line. SMA is probably going to do so here within the next 5 months or so. That's a really big move. And so what that really does is it both validates the technology on the right, and it also introduces really big competition and really bankable competition. So it's big problems for those startups there on the right side. So obviously, no solution to a solar project or a solar solution is one size fits all. There's different kinds of systems. They've got different requirements, different things going on. And so different products can suit different needs. Here I just outlined some of the differences in the main types of projects that we classify at Lux. I'll talk about our analysis in the commercial space and how we view commercial projects and what wins in the commercial market segment. But I'm happy to talk afterward about our similar analysis for residential and utility scale projects. So before I do show that analysis, just a few things to get out of the way. When we look at cost, we like to look at LCOE, which is the dollars per kilowatt hour that you're paying for the energy that you get, as opposed to the the CapEx, the dollars per watt that we're used to throwing around today. And when we talk about module pricing, we talk about it in dollars per watt. But when you're looking at a system level and you want to talk about cost, I really want to get energy as cheaply as possible from my system. At the same time, when we talk about performance, rather than just module efficiency, inverter efficiency, these are device efficiencies. Power into the device, power out of the device. We're going to look at system level performance factor and how different power electronics architectures are going to change the power out of an array versus power into the array. There's also certain things being thrown around: grid-friendly features, compatibility with smart grid, yada yada yada. That stuff, everybody likes to talk about it. It's the benefits of their product and how friendly it is to the grid, and I'm sure Todd here will explain a little bit more about that. One of the other hot topics in power electronics is component substitutions or eliminations, cooling mechanisms. These are things that sort of factor into reliability, which, as I'll show in a figure later on, is one of the more important, if not the most important, aspect of power electronics. Transformers, talking about transformerless inverters, you can get, higher efficiency, but the question is whether or not you're going to be allowed to do that and still connect to the grid. And then capacitors, this is the big thing in the microinverter space. People love to talk about ECAPs or electrolytic capacitors, thin film capacitors. There's a really clear drop-off in performance, but, you get a gain in lifetime when you go to a thin film capacitor. People call this the weak link of inverters. And it's pretty interesting. We're starting to see some academics kind of try and address the problem. I think there's a group at Case Western University that's trying to develop a titanate capacitor specifically for solar inverters, which is really interesting. They're trying to revolutionize or change what's been a conventional electrical component for many, many years. So this is our performance factor monitoring or modeling of systems using different power electronics architectures. The things to note are that we're going from just a system with a central inverter all the way down to a microinverter. The central plus MPPT data point, that's string level MPPT, and then string plus MPPT, that's module level MPPT. One thing to note is just the jump from a system with just a central inverter when you add MPPT, and the same thing when you've got a string inverter. And then also note that we view microinverters as kind of being middle of the pack when it comes to commercial installations. And you can see the breakdown based on how we model that out, where the losses are from array to combiner, combiner to inverter, inverter to grid, and then the performance factor there in yellow. And the reason why I say, watch the jump is because, when we talk about overall cost, then, the capex, which is shown in the bars on this graph, is, slightly higher when you add that MPPT, but the LCOE stays the same, which means that, the added performance and capex kind of cancel each other out, and you're still getting energy at the same LCOE. Obviously you're getting more of it, which is a good thing, but, you're not paying less for it. And then, like I said, microinverters, because of that extra capex, at least now, they might come down over time in cost and price. We'll see. That's a debatable topic. We view them as just way too high based on the initial capex. So this is the results of a survey that we did late last year. Basically, I called up a bunch of project developers and technology providers and said, what's the most important aspect of inverters? And surprisingly, everybody said reliability. Usually, in my experience with market research, it's cost, cost, cost. Here, it was reliability, reliability, reliability for the most part. Cost came in, a little bit in the biggest area for improvement, but most folks are concerned on, whether or not their product is going to last, 25 years, match the system lifetime, and that they'll have to, go visit it or perform maintenance infrequently. And one of the big problems here is that it's tough to compare apples to apples, a system with microinverters versus a system without. I know SunEdison has done a little bit of work here or contributed to studies in the area. Still, mean time between failures, very few people understand that metric, if at all. Failure rates, these are good things that we can show, but it's tough to compare, a system level, something, that's got to have a microinverter for each module versus, something that might just need one central inverter, be able to compare the reliability or the, how often you might need to perform maintenance on each of these two systems. And that's what I mean when I say few metrics, if any, account for the different number of devices required. So now we'll look at the competitive landscape. This is the juicy stuff, which companies win and which don't. This is something that we specialize in at Lux. There's a bunch of these, startups. Defining a startup is difficult. I classify Enphase as a startup because they've been around since 2006. Basically anything after 2000 I would call a startup in the space. These are just a few, certainly not all, but there's a bunch of them out there. Even more, 5 or 10 new ones popped up in Intersolar last week. To steal a legal term, the burden of proof there at the bottom. What I mean by that is, startups really in any field have the burden of proving that they aren't, competitive with incumbent solutions, but that they're better. So these guys have to really, one up everything else, either on cost or performance, preferably both, as opposed to just competing. Right now, on cost, they certainly do cost more, be it hardware or just the lack of scale. They've also got the burden of a different, sort of unique burden of proof that kind of ties into reliability. One of the big selling points for these products is that they're going to offer a 25-year warranty, where most of the string and central inverters are 5, 10, 15 years. Offering a 25-year warranty is great, but you're a startup that's been around for a couple of years. How do I know you're going to be around in 5 to fulfill that warranty, if something, does go wrong in the system? So they've got to prove quite a bit, and, getting onto the bank's approved list is certainly no easy task. So back to this graph, this is kind of the way things are. One of the things that, we think is going to happen as things shake out, because not all of these startups can really survive, we think. Again, I could talk more about, our analysis in other areas besides commercial. We think, microinverters and module level management really works well in residential, but maybe that's it. So, they're going to be competing for less market share than they probably assume. We think a lot of those companies on the right are going to fall out. Certainly not all. There's companies that have been around for a while and have a leg up on everybody else. But we think a lot of those companies go away. And I think a lot of, not a lot, but maybe a couple more of those companies on the left side kind of move into the middle with Power One and SMA, broaden their product lines. There's no reason for them to drop their string and central inverter products. But adding a microinverter to be able to suit every kind of system out there, I think when SMA does it, everybody else kind of says, okay, this might make sense. So in closing, don't believe the microinverter hype for the most part. Like I said, we do think that they fit well in residential systems, particularly ones that might be susceptible to shading or other factors. But we don't think there's going to be a microinverter on the back of every panel in 18 months, like some people would have you believe. And because of that, a Darwinian market is going to emerge on the right side of that Venn diagram. The strong will survive. The rest are going to go away. Multiple sourcing will continue to rule. The same way we've been in the module market, people buy from many different suppliers. They're going to continue doing that with inverters. I think supply issues might have shaken that up in the last few years, but that's going to keep going. We don't think we're going to see many exclusive supply agreements. Reliability will remain the hot issue because, like I said, it's tough. There's not really a specific metric that you can throw on your spec sheet, like a CEC weighted efficiency to measure the reliability. You can only say, show prior data, or say you're certified and you're rated for these conditions, yada yada yada. But particularly those startups don't have 25 years worth of data, so you're kind of taking it on faith when they say that they're going to last and be reliable. The wild card in this space is the big companies. GE, ABB, Siemens, they've all got the capability to make really, really big impacts on everything I've just said and kind of shake up the whole solar power electronics market as we know it. So it'll be really interesting to see what they choose to do. They're kind of in the space already, they've dabbled, but to see if they make a really big play and a really serious move here over the next probably year or two, they could seriously impact things, and it'll be interesting to see what happens. That's all I've got. Thank you very much.
That was great, Matt. That was a great snapshot into the emerging or the emerging landscape of power electronics. I'm hoping everyone is getting their questions prepared. What we'll do is we'll go through all the speakers, and then we'll have time for questions at the end. So our next speaker is Oleg Popovsky. Oleg develops and manages strategic alliances and business opportunities as business development manager for SunEdison Canada. He works with Ontario's municipalities and local distribution companies to develop mutually beneficial solar programs for Ontario's school boards and educational institutions. Previously, Oleg worked for EMC, where he held a variety of management positions. So please welcome Oleg. Thank you.
Good morning, everyone. If you guys don't mind, I'll be roaming back and forth because I always feel like I'm stuck behind this podium. First and foremost, I wanted to thank MaRS for organizing this event. I feel always so energized when I enter the MaRS building. It feels like lots of smart people, lots of analysis, lots of thought. So as JoAnne said, I'd be more than happy to answer some of your questions. Usually this talk does, I guess, drive some questions. I'm very excited about the topic, beyond the solar module. It's a big topic for us this week as SunEdison announced our panel plant and showed off their beautiful new panel this week. So it's quite good to talk about what happens beyond the solar module. And optimizing system performance and ultimately maximizing revenue is really what salespeople talk about. I have to say, though, as I joined the solar industry coming out of the IT sector, that was the big unknown to me. I really didn't understand what happens next. So you build a solar system, it's up there, there's really no blinking lights as IT people like to see. There's really nothing taking place other than it absorbing some sun and hopefully producing some energy. So as I was going through my training and through SunEdison, that was my reoccurring question. So how do we make sure that this thing ultimately operates at its peak and allows us to maximize the revenue streams? Before I get going, though, I'd be curious to ask, how many of you folks here actually own a solar system? All right. How many of you folks are integrators and build these systems for others? Okay. How many of you finance these systems or consider financing these systems long term? All right. So we have a bit of a mixture of people here. I thought that, I'll throw out some of the key questions that come from these various groups, as those are the key, I guess, stakeholders in the solar game. How do we increase the revenue streams of solar is really the big question on the financing side. Solar is a very capital-intensive business, so you need a lot of upfront financing. Matt already threw out there this term of bankability. How do we make the system bankable beyond just the solar components. And then most importantly is, how do we limit the risk? I'm assuming that most of you are familiar with the feed-in tariff in Ontario and know that there is this proposition of leasing a rooftop and therefore minimizing the operational risk to the host, to the landlord or the tenant in the building. And so we are oftentimes asked, so how do I make sure that my lack of expertise in managing the system does not impact the revenue streams from the system? These are some of the key questions that I'll be trying to respond to throughout my presentation. Just to put things in perspective, I get paid by SunEdison, not necessarily here today, but in general. So I have to provide a bit of an overview of who we are and why it makes sense for me to talk about this topic. I'm here actually speaking on behalf of the services group of SunEdison. And the services group has a very clear mission. Our mission is to make sure that solar becomes a meaningful source of energy. So we focus on increasing power generation. We focus on increasing the financial benefits to our investors and our clients, and ultimately making sure that our systems provide a clear impact to both the environment as well as the local economy. Now, just to put the numbers in perspective a bit closer, we have more than 500 systems operational that we actually built or developed, built, financed, and now own. And here's a quick breakdown of the systems. But the most, I think, impressive metric here is the 600 gigawatt hours of energy that we've produced today. If you ever are curious, feel free to go to our website, top right corner, you'll see a counter that's actually a real counter. It's not some IT algorithm that's running up some numbers. And final slide on SunEdison, again, to put this in perspective, is these are the types of systems we monitor. Top left, you'll see the largest system we've ever built, which is a 72 megawatt system. Most impressive story about the system is that it was built at record time, under 6 months construction time. We're talking about close to 300 acres of land. This is in northern Italy, in Rovigo. The system was also built at grid parity. So for all of you researchers, we're talking about, at what point in time we'll be able to develop a solar system that will actually be functioning or installed at the cost of actual energy. Here's a perfect example for that. And then throughout the slide, you'll see a few typical SunEdison systems. Again, we're considered the largest solar services company in North America, so you'll find those. But just to provide you with a range, we have systems installed anywhere from the largest European system, which is Rovigo, to 12 kilowatt systems, or microsystems as we know them here in Ontario, in residential spaces throughout the US. So the two things I'll be talking about is solar monitoring and what goes into our solar monitoring strategy and offering, and then, as you see grayed out for now, the solar operations and maintenance strategy. My slides will definitely not be as analytical as Matt's slides, but I thought I'd throw out one graph so I at least appear smart. When we look at solar energy production, you have to have some sort of concept of rationalization. So what we compare or we define is this OPR, or operating performance ratio. The operating performance ratio is ultimately understanding how much energy has been produced versus how much energy was supposed to be produced, and then taking into consideration some of the environmental factors, the irradiance on site, the weather conditions on site, et cetera, et cetera. And truthfully, this is the only way to rationalize whether or not a system is performing at the peak you needed it to perform in order to achieve the returns on investment that you're seeking. So if you take a look at this graph here, you'll see a month-long analysis, or OPR analysis as we call it, that shows you exactly, and this is the black, I don't know if you can see this well, this is the black graph, what the OPR ratio points were. So certain times of the month, you'll see that there was a drop in energy production, and then there's, in orange, a delta in what it was supposed to be produced, but that's usually due to the fact that we had bad weather or maybe some clouds, despite the fact that overall irradiance was decent, and so on and so forth. So you'll see that throughout that month, and this is 2010, it looks like it's June, we were able to produce at about 100%. 100.6% to be specific. So even though the graph looks fairly inconsistent, this measure allows us to understand that overall, the system in fact produced exactly where we hoped it would produce, despite of the variance in weather, despite of the variance in system performance due to inverter hiccups or whatever might have happened on site. And really, this is the key metric and measure for us on the monitoring side. So I thought I'd provide you with some of the key components that make up SunEdison monitoring system. As Matt clearly laid out, the inverter is the second most important component to a solar system, and definitely second most pricely component to the solar system. And most of the early adopters of solar systems usually leverage the feed coming from the inverter to analyze whether or not it's ultimately producing as much energy as the investor or the system owner or the host was hoping it would produce over time. We don't actually believe so. We think that you need an additional measure on site because the inverter is a single point of failure or multiple points of failure if you're talking about microinverters, and ultimately provides only one source of information. So we deploy what we call a SEEDS or SunEdison Energy Data System Gateway that collects and stores data. For you IT guys out there, it's essentially a server. A server that collects all the data from the various receptors. Then we have an electric meter, most important to the bankers in the room or the financiers in the room. This is a revenue grade meter. So essentially this meter allows us to measure the energy feed within a certain variance of percentage. Then we leverage weather stations. This is a huge knowledge point for me because the weather station is not just deployed as a regular weather station, but we also measure the irradiance, we also measure the cell temperature. And then we compare these factors with other feeds coming from similar sites around the globe. This is what ultimately makes this whole thing a relevant and rational process. We then use a cellular modem that allows us to communicate on a separate communication basis from the inverter, put this whole thing or connect this whole thing via a fiber switch, fairly simple component, into a weathered enclosure. So this enclosure will allow us to monitor the system for 20 years regardless of weather conditions on site. The next step is then our Renewable Operations Center. And again, I'll reference back my IT experience. There's nothing more important in any system monitoring than a smart monitoring team. Similar to the IESO in Ontario, our Renewable Operations Center monitors all of our systems globally on a 24/7 basis. We have actually 3 of these Renewable Operations Centers so that our systems can follow the sun, or our monitoring can follow the sun. And they're involved in every single step of the system's life, so to say. So during the commissioning of a solar system, our Renewable Operations Center makes sure that the independent engineer that comes on site, who gives an analysis of what the potential system output would be from our systems, is in fact in line with what the system is measuring. So that's the validation process. They then prepare the reports that, again, will be compared for banking or expectation purposes. As a next step, and in my opinion, again, the most critical step is where the monitoring and alerting takes place. This is where individual engineers have financial quotas associated with keeping these systems up and running. So again, if you look back to the ISO or other operating teams, I suppose, this is the only and I guess the most important way to make sure that your system is up and running or client systems are up and running. These guys detect and diagnose outages to identify underperformed reports, but most importantly, they define various algorithms that allow us to compare these systems so that we know at what tilt angle to install a solar system in a certain geography. When we came to Ontario, we had to analyze what type of tilt angle makes most sense given the weather patterns in Ontario, and we compared our systems from New Jersey, Connecticut, and so on as a result of having this type of data feed. Next step is the dispatch process. This is where we involve our partners and leverage some of our field crews to dispatch in case we do see some unusual behavior on site. Unusual behavior can be caused by all sorts of issues, as extreme as vandalism, because solar systems are becoming relevant and hefty and expensive, as simple as inverter hiccups. So we have the ability to see within literally a 15-minute interval what happened on site and whether or not the system is performing according to the weather feed, and then dispatch a field crew to make sure that the system is up and running properly. And then last but not least, provide analysis. This is where the financial clients are really focused on getting their return on investment, because they can ultimately see whether or not the performance of the system yields the type of revenue streams that they were hoping to achieve. Now, interestingly enough, this is, as much as Matt talked a bit about the infancy in some ways of our industry and the startup mode, it looks pretty sophisticated, I think, when I show it on the slide, but the reality is this is fairly new to the industry as well. Last year at Solar Power International, I was going around and chatting with some of the colleagues and trying to understand who else does this. And truthfully, around the globe, there's very few companies that actually go to such level of extent to understand or to analyze and understand the system performance. And so pretty proud to see the advancements made in Ontario. The folks from the Courtright Centre who have their trailer right outside, they're making some serious strides to create some standards in the industry and help clients like yourselves understand what's real, what's unreal. There's a lot of other innovative approaches, and I really hope that some of the outcomes of this conference or of this event this morning is you folks thinking about how do we improve the process, how do we make sure that we have smarter, more efficient monitoring systems out there to ultimately help make better decisions around solar energy. We then use a platform which is a portal that I'd be glad to walk most of you guys through. It's an online portal that we log our clients in that ultimately shows you exactly how much energy has been produced on a daily basis, on a monthly basis, and so on. That graph that I showed earlier was pulled from a monitoring system. So in the top left, you'll see just a snapshot of a daily production. It's maybe tough to see from far away, but essentially it shows you a nice bell curve that must have been a good sunny day when that picture was taken. Then you'll have a clear insight or transparency into the feed-in tariff revenue as it's relevant in the province here, and so on and so forth. So you'll get an understanding and appreciation for the level of sophistication that we can get to as a result of the monitoring components that we have on site. So now that we have our system fully monitored, what happens next? Really, the goal of operations and maintenance, especially over a long period of time as 20 years is to increase the returns by driving production. As I mentioned, the folks that we have monitoring these sites, and this is a real picture of our operations center on top right there, they are financially tied to making sure these systems are up and running. In fact, I was pretty blown away to hear that SunEdison has received, I think, the 3rd or 4th award over the last a couple of years of Solar Power International for keeping our systems up and running for more than 99% of the time and at 109% of system output. The reason I was pretty blown away because for IT purposes, that's a joke. If you in IT let a system run at 99% of the time, you will never get another order from another client. That's simply unacceptable. We're talking about 5 nines availability. We're talking about completely different standards. But in the solar industry, believe it or not, in California, the average system uptime is around 78%. So factors like the ones talked about by Matt in terms of inverter, consistency, uptime, and sophistication are what goes into it. So we go through various standard procedures such as semi-annual cleaning and so on, and ultimately come to this very repeatable, very consistent process that allows us to overall optimize system performance. We then dispatch our field crews to make sure that there's preventative maintenance taking place. And from what I've learned now is that this is really the key component because there's, again, somewhat of a lack of sophistication in the industry. We don't necessarily know when a computer system is about to fail as we do in the IT industry. We only know that we need to go on site and make sure that all strings are checked for, that there is no animals chewing their ways through cables and so on and so forth to ultimately ensure that the uptime of the system and the overall performance of the system is driven over and over again. And then last but not least is cleaning. We're fairly fortunate in Ontario in that we have very little soiling. There's no real desert storms or so taking place around us, even though I'm oftentimes blown away by the weather changes that we have from winter to summer. But the cleaning aspect of these systems is key. And there's some really interesting new and innovative companies now popping up all over the place in Ontario that offer all sorts of solutions for washing solar panels. Let me tell you, my folks say that water is the best. It's the best way to solve the cleaning problem. So cleaning of panels is key, and I'm showing some pictures here. These are actually real pictures from competitive installations, as you may imagine, of vegetation and dirty panels. This is real. There's literally systems out there. I think some of them are in Ontario that have been there for some time because maybe some hobby guys put them up, and they've been forgotten about. So people don't monitor the performance. They don't really know how much they're losing out by simply not cleaning the panels or not taking care of the vegetation around it. And when we talk about bankability, I thought I'd just provide a quick snapshot or summary for the types of funds that we've been able to set up ultimately as a result of this strategy, as a result of our ability to convince banks who are generally fairly conservative, especially some of the European banking firms you'll see out there, to invest in solar systems with SunEdison. I truly believe that the maintenance and operation strategy is a key to the overall success of making solar a real and relevant source of energy. So I hope this provides a similar perspective as a result of my presentation here. Just a quick snapshot. Like I said, to work for SunEdison, I have to kind of let you know who it is that leverages our systems. And if you have any questions, I'd be more than happy to answer them afterwards. Thank you.
Well, thank you, Oleg. That was great. In fact, I happened to be out at your opening of your new solar plant in Newmarket on Monday, and congratulations. It was an excellent event, and it shows the commitment you have to this province. I really enjoyed the operations and maintenance discussion. You know, so often the real sexy part's the project and getting the contract, but at the end of the day, these facilities have to be operated and maintained in incredible condition for 20 years so that the pro forma will be reached and the bankability will be maintained. So that was great insights. We have a final speaker, Todd Williams. Todd is Managing Director of Navigant Consulting's Canadian Energy Practice. He has advised numerous developers and utilities on renewable and clean generation opportunities. Todd also just recently led a study to determine the capacity for renewable generation to connect in Toronto Hydro system. So with that, we'll welcome Todd.
Excuse me. Thank you, and good morning. It's great to be here. What I'd like to do is just cover off 4 things, but I want to start with a question. Oleg asked, I think, 3 questions. I'm going to ask one more question. And how many of the people in the audience have an application in but an inability to connect to the grid? I wasn't counting hands, Oleg, but I think it's about a similar size group as what you had. What I won't be able to answer all your questions today, nor tomorrow, nor next week. I've got a 10-minute slot, and what I'd like to do is actually just give some perspective in terms of what's happening, like the reasons there are capacity constraints, talk a little bit about some of the steps the industry is doing, and also just for the, given this is MaRS in terms of innovation, new opportunities, I just want to present one opportunity for maybe there's someone in the audience, maybe it has actually to do with power electronics, I think, and communications. I know there's a number of those that relate to capacity constraints. So let me go through just a quick overview of Navigant firstly. Navigant is a consulting firm. We have about just under 2,000 people corporately, and we have about 250 in the energy practice, and there's about 60, actually I think the number's more closer to 80 now, who just focus exclusively on renewable energy. So we do quite a lot of work in renewable energy. We also do a fair bit of work in clean energy. And this is just a list of the types of services that we provide to a broad range of clients. In terms of background, some of this I suspect a lot of you know, but there has been a tremendous response to the FIT program that JoAnne discussed earlier. What that has done, though, is it has created some generation connection constraints in Ontario. The system, the transmission and the distribution system, in a sense, is designed to flow power from central generators to customers to this building, for example. The response to the FIT program has put a lot of new stresses on that system because, in a sense, they're asking it to run backwards to some extent. Given its service territory and the suitability of wind and PV in that territory, it's not surprising that Hydro One has had the bulk of the connection request. I mean, the LDCs have had a lot of, the other LDCs across the province have had a number of requests, but certainly the expansiveness of Hydro One's territory, they have received the bulk of the requests. The other interesting point to make is that given the topology of the system, the transmission system, most of which in Ontario is operated by Hydro One, serves the distribution system, all of the LDCs. And if there are constraints upstream, those can affect what happens downstream. And that's one of the most interesting things we found in the work that we did for Toronto Hydro, is the constraints upstream can have a significant impact and can actually drive most of the constraints downstream. So that was an interesting finding for us. You hear, I don't know if those of you who said, you raised your hands and said we couldn't connect, if you understand sort of why and what the reasons are, is it just someone saying you can't connect and that's it? What I'd like to do is just walk you through kind of the physical reasons that the system cannot, some of the reasons why the system cannot connect renewable generation. So starting from, and these are physical reasons, physical or electrical. Starting from the left-hand side, and this is information taken from the Hydro One website. And we did our analysis on it. Someone else could do it slightly differently. They'd end up with different numbers. If Hydro One is here, they may have different numbers, and they're free to disagree with me. But I just want to present these as illustrative, sort of directional. But the relativities, I think, are pretty much there. If we start on the left-hand side, there is a constraint in terms of basically how much current you can flow on a wire. It's the same as your house. You know, most of your circuits are limited to 15 amps. It's no different than for any distribution or transmission, whether it's a feeder or a bus. And the capacity, if you just look at that and said, how much can I flow on those wires in terms of connecting renewables? It's about 18,000 megawatts. Pretty big number, lots of room. If you look next, if you go to the right, there's a reduction in that's driven by short circuit capacity. So short circuit capacity is when there's a fault in the system, the generators, and I think a lot of the inverters can have discussions in terms of how much they'll contribute. But when there's a fault on the system, the generators basically try to fill that fault, and they pump current up the line across the network, and all the components in the system, throughout the system, they all have fault current limits. And if those fault currents are exceeded, they either explode or they fail. And so it's not only it's a reliability issue, but it's also a safety issue. So if that happens, that's not good, obviously. So Hydro One has looked at their system, and they've said, these are the limitations with respect to short circuit capacity, and basically you end up losing about half of the available capacity because of short circuit constraints. You lose about 9,000 megawatts. If you then go to the right one more step, some of the Hydro One transformers have constraints with respect to power flowing backwards. If you recall, I mentioned, in essence, the system was built to take power from the central plant, distribute it to customers. In some cases, if you put too much in at the low end, you're going to actually ask the transformers to operate in reverse, if you will. And many of the transformers are not built to do this. And again, so there's a reliability, and I suspect possibly a safety issue. But in this case, that constraint, minimum load, not letting transformers run backwards, you lose about another 5,000 megawatts. So what started with a thermal capacity, basically how much the wire could carry of about 18, you have two factors that constrain it. One related to short circuit, another related to minimum load, and you end up with just under 4,000 megawatts of connection capacity. I also want to point out that this was a relatively simplistic analysis, and there's probably a lot of other factors. There's contingencies, there are other constraints that probably reduce that 4,000 even more. But I just wanted to show you the steps, sort of the sequence, and if you're sitting here in this building and you said, how much could I connect on the roof? You'd look upstream in terms of the network, and you'd say, what is the lesser of those constraints? What is the most constraining factor? And that's what drives it. So in this building, it could be short circuit. I suspect it would be. Somewhere else, in rural Ontario, it could be minimum load. So it depends where you are, depends what the network is, but these are the sorts of constraints that it can affect, and those are the reasons why someone told you that you could not connect. Now what's interesting, excuse me, if you look, we've got the same 3745, about 4,000 megawatts of capacity. That's what Hydro One is saying now is available in their grid. In terms of people wanting to connect to the grid, there's about 4,000 megawatts, the red bar there, that have applied and I think in many cases received approval to connect. And I think it's probably not coincidental that those numbers are pretty close. It could be coincidental, maybe it was just the way the numbers worked out. But I find it quite interesting that that's the capacity, about 4,000. We've got about 4,000 that has applied and in many cases I believe received approval. But what's most important for us in the room is there's about 7,000 megawatts. You can probably see, some of you who've raised your hands can see yourself or your projects in that green blob there, green block, that cannot connect because there's not capacity on the system. So that's really the, I guess it's the response is, is great, but in terms of the system is certainly constrained, and it is truly constrained in many areas. What's happening in the industry, and I think, I think a lot of people may, talk about, Hydro One and why couldn't they do anything faster, and at one point I thought that, but at the end of the day, I think there's 25,000, JoAnne, is that, it's a significant number of applications. And for Hydro One to look at each of those individually and sort out what needs to be done, it's just a significant, obviously a significant resource issue for them. But I think it's good. It's good that the industry and Hydro One are now working collaboratively, one, to better understand, and hopefully to address the constraints. And these are just some examples of some things that are currently underway. So firstly, Hydro One and CanSIA have established a working group, and they've retained a consultant to explore the contribution of PV to short circuit levels. And if you recall this, let me go back. If you recall this chart here, that's where we lost about 9,000 megawatts of capacity. So there's a big question about whether an inverter contributes, say, 1 times its power rating, or 1.1 or 1.2 times its power rating to the short circuit levels. So there's a discussion underway, and people want to get a better understanding of that. Hydro One is also said to be revising or revisiting its 7% rule. And that 7% rule, again, they've got a big system, and the rule they've established, which I think is reasonable, is for small fit applications, for small PV, it cannot exceed 7% of the maximum load on the feeder. And for them, it's a safe uniform level to set. And as I said, if they went beyond that, it's going to be a heck of a lot of work, and actually it requires resources and information that I'm not sure is readily available. But they are supposed to be revisiting that, and to the extent that that number changes, hopefully it increases, that would create a fair bit of room. CanSIA has also proposed a inverter workshop, so all the parties can better understand how the inverters work and how they interact with the market. There's been a proposal for testing of inverters. No surprise, it's interesting, we talk about panels here and inverters here. It's the inverters that are really the connection to the system. And no surprise, that's where the focus of this effort is in terms of what do these inverters do to my system in terms of short circuit? What do they do in terms of, say, anti-islanding? How do they respond to high voltage? Do they contribute? All those sorts of questions. So a lot of it is, not surprisingly, focused on the inverter, because that is the connection of the module to the grid. And there's also a growing recognition of high voltage issues. In some cases, it's causing trips. The systems aren't meant to feed into a higher voltage than they expected, and they trip out, and that's causing, back to performance, that's causing a lot of issues in terms of performance and output. So just to summarize, excuse me, I think it's fair to say that the industry knows more than it did a year ago, and I would say that, frankly, given the stuff that's underway, the activities that are underway, they'll know a lot more a year from now. And the other point to take away, if you can't take anything away from what I've said this morning other than one point, is that it's very complicated. And again, I'm talking very briefly this morning, and probably someone who knows a lot more than I would could talk for a couple days on the topic. This is MaRS, and I think John mentioned that one of the objectives of MaRS is to encourage innovation in Ontario. And I just present here one potential opportunity that I see, and I think actually it's representative of the types of opportunities that there would be for this market. So let's just look at the minimum load constraints. So in essence, if you recall, I talked about the minimum load constraints being we don't want power flowing backwards on our transformers, which is fair enough. Some of the transformers cannot handle it, and it's causing a reliability issue. But what's interesting is when you look at the typical load profile, consumption profile pattern for Ontarians, any feeder, it's generally peaks during the day or later in the evening, and PV output, no surprise, peaks around noon. So when you look at this, most of the minimum load occurs, say, 3 o'clock in the morning. So for PV, it's a completely different concern. I appreciate the concern with respect to, say, a combined combined heat and power or cogen facility that wants to run 24/7. They'll be on at 3 o'clock in the morning. I'm not aware of any PV panels that are on at 3 o'clock in the morning unless they're in the polar regions. So if we look at I've referred to the Hydro 1, the 7% rule. So the PV cannot exceed 7% of the maximum loading on the feeder. So what I took is just sort of we have different feeder information for all hours of the year, 87, 60 hours of the year, and I sorted that from highest to lowest. So at say this hour today, that might be halfway down that curve, and we had a simulated PV output given the weather, and I think this was 2009 data we used. So we sorted the transformer load. This is a bus load, which is actually an aggregation of feeders, but just imagine it's a feeder. We sorted the load from highest to lowest, and we looked at the solar output, the predicted solar output at that particular hour, and what you see is that's all the green spots on the bottom, right? So there's 8,760 green spots there. Many of them are zero because at night there's no output. So what's interesting to look at here is that limit, 7% of maximum output, there's an awful lot of headroom between the maximum that the PV would be and the lowest level. So on this particular chart, I don't see any point at which the PV output is exceeding the loading. So it's definitely a safe limit. Is it conservative? Probably, but it's certainly safe. What if, for example, I said, I don't want to be so conservative, I want to bump it up a little bit, and I said, I want to get 8 times as much. So let's have a rule of, 56, right? So if we went to a 8-fold increase in output to 56% of the maximum feeder loading, still doesn't exceed it very often. It does 28 hours of the year. So that's the points to the right-hand side, just above the curve where the solar output is higher. Those are the hours when it would be backfeeding, if you will, or in a sense running the transformer in reverse. Now, in order to do that though, I think from a safety perspective, if we had a perfect system, we'd look at that and we'd shut down the PV at that point, or we'd dial it back to be just below the transformer loading. Then the system would still be safe, and I got a heck of a lot more PV capacity on that line. It'd be in this particular case, another 28 megawatts. But what that would require is, it requires understanding the load on the bus, and for Hydro 1 system, I'm not sure that they have that sort of information live for all of their transformers, all of their feeders. So one, you have to understand the loading on the bus, you have to understand the PV output, and the other thing you have to do is control the PV output, or at least dial it back somehow to manage below that. And just from a developer's perspective, if I was told, if I'm the one that is just above that line and I've been told I can't connect, I have no project. If someone comes along and says, well, we have a way for you to connect, it's going to cost a little bit more, we need to apply some technology, that might be worth it to me, even if I get dialed back for 28 hours of the year. So the question is, how much would you be willing to pay as a developer, and what would be the market opportunity as an innovator to develop this sort of technology? So in conclusion, there has been a tremendous response to the FIT program. It has caused and it is creating some generation constraints. Typically, those constraints are driven by the most restrictive of generally three factors: thermal load, short circuit, which is a fault current, and also minimum load, and there are others, and they sort of work together, sometimes in weird ways. So the capacity of generation wanting to connect is much greater than the capacity that's available in the system. The industry is working together, and it's a very complicated topic, and I think that a lot of people are sort of learning new things as they dig deeper into this stuff because they never had to in the past. And I think from an innovation perspective, there are many opportunities for smart solutions to enable connections beyond what Hydro 1 and I think some of the other LDCs have set as kind of safe, uniform levels. So I thank you for your time and look forward to any questions.
Well, that was great, Todd. Thank you very much. Yes, I am more than painfully aware of the connection and constraints issues in the province. But we are working collaboratively with Hydro One, with the LDCs, with government, and that was an excellent potential opportunity there that's certainly worth exploring, and I hope you're talking to Hydro One about it. I would also like to say that if any of you do have a PV contract with the Ontario Power Authority and you're producing at 3 in the morning, we're coming to find you. So now I think it's time for questions. There's 2 mics on either side of the room. We'd ask you to go to the microphones. There's also, we're streaming this presentation, this breakfast, over the web, so there may be some questions come through the web that we'll take. I think we have maybe 15 to 18 minutes for questions before we close things out, and away you go. Mr. Love.
Peter Love, Hydro One Research Fellow, formerly a colleague with JoAnne's at OPA. I'd like to ask the panel for their thoughts on grid parity, and I'd just like to limit it down. Let's exclude residential, and let's exclude utility scale. Let's look at commercial operations, and let's assume, I don't know, marginal cost of generation in Ontario, 10 cents and another 5 cents or so for transmission and distribution. So let's say marginal cost of a commercial would be in Ontario 15 to 20 cents. I'd be interested in your thoughts of when you think system costs might approach that level. I know people are talking about grid parity in California in a few years, and just be interested in your perspectives on when you think we might be. And JoAnne, if you'd be prepared to comment, be interested in your thoughts as well. But
Just the moderator.
okay, fine.
Yeah,
I guess I'll take the first stab at it. Interestingly enough, this is the most reoccurring question in the industry.
Yeah.
As I tried to hint, I guess, during my presentation, we have hit grid parity in various geographies. At 24 to 25 cents kilowatt hour, we are at grid parity. In California, in Germany, in Italy, in certain parts of Italy to be specific. So to answer your question, as the cost for system components or installed cost for system components is dropping faster than we can sometimes hold on to our own pants, grid parity is becoming more and more real. If I was to pull out my crystal ball, I'd probably suggest within the next 2 to 3 years max in Ontario.
Great.
So first of all, we do see grid parity in the commercial segment as the nearest, obviously, because the rates are or system costs as a function of watts based on capex and LCOE. It tends to be the lowest because once you get into the utility side, you're looking at the wholesale rate. We agree that it's happened in Italy in a few places. As more of a conservative analyst, we see prices, and based on our pricing surveys, dropping, but not dropping as quickly as others do. We're more of a 5 to 10 year to grid parity, opinion specifically for Ontario and for most geographies. We've really seen it only in Italy and a few select other places like Hawaii, where rates are just through the roof. But we're more of a 5 or 10 years for Ontario. That's our projection.
I would be inclined to agree more with Matt than with Oleg in terms of timing. I think 5 to 10 years or so. And you gave the assumptions in terms of 10 plus 5. And that's your key point, is the 5 is included in the commercial, where it's not in the wholesale. So.
Okay, thank you.
Yeah, maybe could you introduce yourself as well and who you represent?
Clemens Zanzel, I'm the former president of SACON Power Systems, one of those inverter companies up on the board, also doing a startup in this area as well. But the quick answer on the short circuit, you should use 1.25, period. Inverters don't add short circuit. That's really a red herring. But the question I have is on the grid, the 7% rule. I agree with you, the 7% for solar doesn't make sense. But you have to look at other limits. I'm wondering if you looked at other constraints that you didn't have listed, such as grid stability. And grid stability, most people believe, without adding distributed gas turbines, and now you can buy fast response gas turbines from GE, for example, or electrical energy storage. And I'm leading 2 projects in the U.S. with the U.S. Department of Energy. One of them will actually, the outcome will be how much storage you should put on a power plant to maintain grid stability. But most people believe that 10-15% penetration of renewable energy, it's very grid dependent. In Ontario, that's going to be a lower number than a stiff grid in Europe. But Ontario's probably like 10-15%. And have you, just wondering if you've taken a look at that for the Ontario grid? What point do we hit a grid stability issue? And all these other discussions then will quickly turn to how much electrical energy storage are we going to put on the grid, or how many more gas turbines are we going to have to build to stabilize the grid. My personal view is it's absolutely an oxymoron to put renewables on the grid and then build gas turbines to stabilize. It really should be done with electrical energy storage.
All right. It's a very good question, and the numbers and the approach that we took was completely independent of grid stabilization or any issues around that. It was really just looking on a feeder, so forgetting about what the neighbor feeders are doing or the neighbor transformers are doing, just looking there, looking upstream, saying what are the constraints. So the numbers we're presenting, again, were estimates based on information from Hydro One website, and people can sort their numbers different ways, but I think the relativity is still there. With respect to grid, so we did not look at grid stabilization. With respect to grid stabilization, you're absolutely right that it is dependent on the individual market, and actually what are the characteristics of the generation in that market. Ontario has a fair bit of hydro, peaking hydro, fair bit of gas capacity now. And again, we have not specifically looked at that of late in Ontario, but the numbers that you're quoting, sort of 10 to 15%, seem to be what a lot of other jurisdictions are looking at. But I haven't looked at the differences in Ontario, whether that number should be higher or lower. But again, I think that where people are looking at now is, can I connect? And it's that single connection. Can I connect to that feeder, that transformer, that bus? I don't know, given the penetration at this point, if it has become an issue. I think it would be someone like the ISO, I suspect, who would be looking at that in terms of, do we have a concern and what types of resources might we need?
So I suspect if they raise the 7% rule to 15, then quickly you won't be able to do that 56. You're going to hit this 10-15% number, whatever it is, on stability, and then somebody's going to have to pick up the cost for that next step.
Yeah, no, that's quite possible. That's right. Again, we looked at it from I just want to connect the feeder, and I don't care. In a sense, we were agnostic to the sort of system stabilization impacts.
Great, thank you. That'd be great to get that number if we could encourage somebody to take a look at it. I suspect the ISO is taking a hard look at that.
Yeah.
Any of you, Matt or Oleg, want to make a comment on that question?
I think we're in general agreement. I think when you talk about the total energy market and grid stability, we tend to use 15% penetration as a baseline, and we start to send up red flags for solar individually when that hits 5% of total consumption just for solar. So that's not counting wind and hydro and everything else. And that's affected our market projections actually in Germany over the next 5 years. We see them kind of teetering over that, getting into the 6-7% range if they keep growing, as quickly as they are. So those are the assumptions that we generally use. 15 sounds about right, though.
Of energy, 5 to 7% of energy.
Total energy consumption.
Total energy. Yeah.
Another question?
David Nixon, I'm with the Solar Energy Program at Courtright. Just wondering, when you're looking at capacity, and I saw in your graph where the output of the arrays is not concurrent with the peak of the grid, have you looked at all at shifting the peak of the output of the array to when the load is peaking? I put up one of our arrays as southwest, and so it's designed to peak the output of the array to the peak on the grid. And the surprising outcome is that since we have parallel arrays, it is actually outperforming the array that's facing south. So that's that's kind of a nice thing. Oleg's looking a little, so my next part of it was, have you guys seen that at all, or have you worked looked at that in any way? I don't know.
Our analysis was sort of, in a sense, kind of optimally situated, optimally oriented, so, primarily south-facing. The point you raise about the facing west, we did not, southwest, we did not consider that. And I would be very interested to know what very interested that you're getting better performance out of that than you are out of one that's more oriented south.
It's preliminary results, like just over the last 3 months, that's what it's done. So over a year, I still expect it to come up short of the south-facing array.
Right.
But, in the winter, that's when it's going to fall back again. But it was,
Yeah.
That's why we did it. And the other part of it is, I haven't heard you mention that about power factor correction, that the inverters could actually be dynamic power factor correction at the load, and that would actually increase the capacity of the grid rather than it being a challenge to the capacity.
Yeah. And I talked about the three primary constraints, and I mentioned that there were others, but those are typically the three that we hear most. And typically, it's never thermal constraints, rarely an issue. I mean, these are generally pretty fat conductors.
Yeah.
It's typically the constraints on a system-wide basis. If you look at the numbers, it's typically short circuit, and then minimum load, and then on a localized basis, there could be just a lot of things going on, a lot of factors, and that's why I said it's very complicated. So power factor could be an issue, and with respect to inverters, I mean, there's a lot of things that the inverters could do to the grid, for the grid, frankly, and I think that there are a lot of opportunities, and I suspect a lot of the firms on his Venn diagram are looking at that. I mean, obviously they need to have uptime and reliability, but in terms of what does the grid need and how can we help to connect more of the PV, the inverter can actually, I think, play a pretty critical role in terms of simplifying that connection or easing those constraints.
Yeah, one of the inverters we're running can do the power factor correction, and so I'm just been wondering what kind of value that would bring. I'm not sure. The vendor says it's of value, but what value is that to the grid? And this is a residential, size inverter rather than utility.
I haven't heard of that as being a big factor.
Okay.
So.
Okay, thanks.
If I may add to, I guess, the perspective, one thing that I oftentimes find missing in the industry is some sort of a collaborative or communicating path between the various geographies that have solar PV deployed. We don't currently really rationalize how Germany, for instance, handles the aspects of stability, grid stability, how they consider the need to modernize the infrastructure, and how the involvement of their feed-in tariff program has changed some of the perspectives. And similarly to your point, I think one of the, or I hope that one of the big outcomes of SunEdison's monitoring work will be the ability to, I guess, look at some of the data that we have and ultimately form conclusions as a result of the various feeds from the various geographies. Maybe that's a task for some of the folks in the room. You're far smarter than most of us.
Hi, Fidel Ryerson with Resco Energy. This is, again, the inverters seem to be a key theme to this discussion, and they play a pretty critical role. And one of the things that surprised me, and Oleg, you may have found the same thing, but it kind of goes to the fact that we're dealing with global inverter manufacturers, and many of them are surprised by the level of detail or requirements that the LDCs are putting on them. Well, we've been involved in a number of conversations where we had to bring in literally the chief technology officer for some of these global inverter companies to discuss fourth and fifth harmonics and have all kinds of interesting conversations, many of which they're surprised to be having with an LDC. It speaks to kind of two things, and I'm wondering if we can maybe put it a little bit in context of how the inverters can help us solve some of these problems as a core piece of this technology. I think David started to talk about it. But are we asking questions as a grid because we don't know the answers and we're relying on their expertise to bring that into us? Or is there a role that the inverter manufacturers can play to essentially discount some of the challenges and move some of that discussion along further by taking the technology one step further than they would have to for the rest of the global market? And I think it's one of those challenges where you don't want to necessarily put it on the backs of the inverter manufacturers, but they do seem to have the ability, and maybe this even differentiates that Venn diagram further, Matt, because it makes it, it's definitely a different level of sophistication that we're seeing in this space. And the surprise is one of the things that I've really taken away from it.
Yeah, and to what degree does it, fall on them? To what degree are they willing to invest, the resources to improve their products for a certain market, right, and to tailor to a certain market? I mean, they've done it broadly in the EU and North America. Whether or not they're going to, take it upon themselves to really, really support the grid, I mean, I think that they understand that they can still sell products and just have them installed and have everybody else worry about it and move on. I think that at the end of the day, all they can do is support. And most of them have some kind of feature that they think will help. But specifically for Ontario, I mean, there's a couple of inverter manufacturers that will definitely show a commitment to the market and will do some things around the market and even tailor their products for the market. At the end of the day, though, I think it's just support. They can't solve any of these problems. We can talk about storage, right, and how that can help solve grid problems, but that's a whole other discussion in another seminar about the cost of lithium-ion batteries and things like that. I think that they're relatively happy with the way that their products have been over the past 30 years for the most part, and as much as they'll try and help, I think that they're satisfied just selling their products the way they are, and they think that they've done enough. They will continue to evolve, though.
Yeah, Fidel oftentimes raises good points. It's one of them. I think it just shows how little rationalization or how little collaboration, again, there is between the various jurisdictions. I mean, if we have industries across the globe functioning where some of these CTOs of the large inverter companies never had to address the concern, and suddenly they have to do so more often here in Ontario than elsewhere, I think it does make the point already. What's interesting, I think, is that the regulations and the standards are so different in all these jurisdictions, and that's what ultimately makes their job tougher, and they have to become, they have to get out of their engineering roles and become better, I guess, salespeople and government relations people to make sure their products find their way to market.
And if I could just add, I mean, when I talked about what's happening in the industry, there was a fair bit of collaboration, which is great, between industry and developers and government agencies. But if you recall, the first thing I mentioned was there was a study related to PV impact in terms of short circuit. There's another inverter workshop, and I think it's essentially intended to help the utilities understand what the inverters can do, and for the inverters to understand what the utilities are asking about. There's another question with respect to inverters and their performance in high voltage. So actually that 7% rule is partly related to anti-islanding performance of inverters in fault circumstances, and whether or not they trip or they protect the system or not. So almost all of those recent developments are all related to inverters, and it's not surprising because that's kind of the linchpin in the thing. And I'm actually quite happy to see that. I think it's a two-way street. Utilities have to understand how the inverters work, and I think the inverter manufacturers and suppliers have to understand what the utilities are looking at and what they're concerned about, so they can demonstrate that their systems, their inverters, can satisfy those requirements.
In Southern California, if I may add, in Southern California, I believe, I think some 2 weeks ago, there was a public webcast and forum where the utility invited some of the larger players entering the market, both inverter and solar companies, to talk about what they're looking for, what support they need, and how to standardize some of their requirements. That's the type of collaboration that I think still is missing, and hopefully we can see here across North America.
I just want to check, are there any questions from the web? No? Okay. So we'll probably take these last two questions. Can you go ahead?
Hi, my name is John Chabuk. I'm a recent graduate from the University of Waterloo. I have a sort of general question pertaining to, so there's basically this, you speak to how there's the energy capacity there, and you have basically this weighting that you can't actually supply back to the grid. I was wondering if there's initiatives out there to basically share that energy in a community environment so that you can basically, so there's that energy there, and like the infrastructure is effectively set up to sort of create energy, but instead of actually trying to seek monetary gain for it and supplying it back to the grid, are there initiatives out there to actually share it to immediate resources effectively right around a given area, someone's home, or if, let's say Walmart has it on their roof, could they share it to other businesses immediately around them?
It's a very good question. If someone is not going to connect to the grid, so if it's either off grid, or they're going to say, I'm going to serve this load in my building, this circuit in my house, my building, with my generator, then that's no problem. I mean, it's one of the most interesting things. People go, well, you can't connect. You can't put that generator there. Certainly you could if you were to take that whole thing offline and it has no connection with the grid whatsoever. But in terms of sharing that energy with others, I mean, that's what the distribution and the transmission network are for. So distribution sort of local area, transmission broader area. But in order to get that energy that's not able to connect to others, you have to connect it. So it's a bit of a catch-22, unfortunately.
To take a bit of a different angle, an interesting thing to look into would be microgrids. I mean, that's
effectively what I was trying to get at.
It's a big military initiative, I think, because of the fact that they can be remote and they might need to generate wherever. It's something that we foresee particularly as military heavy, I think, in the near future. Whether that can be worked out on a more, wide scale sort of commercial basis is yet to be seen. But, the concept exists.
I think it depends on the jurisdiction, the incentive structures that are ultimately in place. In certain parts of the world, net metering in some ways does incent or creates a structure by which you can feed the energy back into the community, I suppose. The other rationalization is, how much of the energy that we feed into the grid, especially in some of these smaller systems, actually ever makes it back into the transmission system, and so on and so forth. But ultimately, it goes back to the efficiency and the capability of the grid to carry the energy, and that is the big, I think the big pink elephant that everybody's staring at is that infrastructure, the energy infrastructure, probably globally, not just here in North America, is so outdated and needs so much improvement that by the time we have done the work that it takes, we should be able to do exactly that.
Thanks.
Todd, any comments? Okay, I guess this will be our final question.
Thank you. My name is David Dunnison. I represent, I have two hats, Q-Cells, as well as one of Canada's largest clean tech venture capital firms, Yaletown Venture Partners. Question with respect to both grid parity and allowable capacity, and this goes to, I think, your second last chart, Todd. If we model Toronto, for example, if you were to install 10% PV by overall demand, really you're just shaving peak. And peak is a lot more valuable than baseload. So when we're doing a grid parity assessment, aren't we evaluating that incorrectly in terms of its true value? And secondly, can't we take this building, for example? There's no way that we could satisfy the load of this building right now by installing PV on the roof and all around the sides. So what is the real issue when it's a rooftop or building integrated situation and these capacity constraints on the grid?
I'm happy to answer that. I wanted to point out one thing, and I forgot to mention it in my presentation, but that if you recall that green block that was the 7,000 megawatts that could not connect, all of that is subject to the OPA's economic connection test, and I expect that coming out of that there will be opportunities to enhance the grid to connect much of that. So I just want to point that out, it's not lost for good. It's just at this point the OPA is working closely with Hydro One. Your point with respect to the timing of it is spot on, and I think that's always the concern you have to have when you look at levelized cost of energy, because there is a cost typically to capacity, and I would agree with you that if it's on peak, you've got the cost of the energy during that period, and you've also got the cost of the peak capacity, the the generation capacity you need to meet your demand.
So Matt, do we bring in the 5 to 10 years if we account properly for the value that PV is generating?
Maybe. This is kind of one of our next initiatives, is to use the time of use pricing essentially that's going on in California and try and find if grid parity comes closer around there. Obviously, it's going to depend by market. You'd have to look into Ontario, and it's my understanding Ontario doesn't have time of use pricing, right?
We do.
Oh, you do? Okay, so you do. And maybe. It could, help out, obviously, in the middle of the day. This gets back into the whole broad, what is solar thing, right? And how it helps out. And, maybe it could. But obviously, in other parts of the day or on days with inoptimal conditions, you're going to have issues and might not be there.
And I would also add, Peter mentioned his example, I think, was 10 cents for commodity and say 5 cents for all the transmission distribution. So I think when people talk about grid parity, at least in that example, it's grid parities from a customer's perspective, right? I can continue, and we've done analysis, and what we look at is a customer building a new building, 20-year decision. Do I go with PV or another renewable source, or do I connect to the grid, right? So in that case, they're choosing to connect or not, and if they don't connect, they don't pay any of that connection charge. There's no 5 cents, there's no 10 cents, and then it's all the renewable energy cost, and in that case, it's the LCOE. But for when you look at grid parity and you say we should consider the cost of peaking capacity, which I agree with, the important thing to recognize is that from an overall societal perspective, the 5 cents for the transmission and distribution, those are sunk costs, and in some cases you're using that power, you're using that network to get the power around to share that with others. So it's not necessarily an avoided cost. So I think you have to be careful from whose perspective you're looking at this from. Customer building a new building, yes, it's fair enough, but societally, that 5 cents is not necessarily avoidable, because the 10 cents is typically the marginal energy cost. Sure, that's avoided if I generate. The 5 cents is not necessarily all avoidable, and I would say it's largely infrastructure costs, and probably only a fair bit of that, only a small portion of that is avoidable. So.
Well, the peak load is growing, at least in California, 2% a year, and here in Ontario, we've just seen the Bruce to Milton line be approved. So. We are absolutely adding capacity every year to deal with peak, both transmission and generation.
No, I don't disagree with that statement. I'm just saying that when you think about grid parity, and I go back to the example that Peter used, 10 cents and 5 cents, recognize that just think about whose perspective you're looking at, and if you're looking at it from a societal perspective, say from a provincial perspective, grid parity, what does it mean? And what costs are we counting, and what costs are avoidable, deferrable?
But when we do think about what it means, I think your point is what we are missing to take into consideration. That's why I'm willing to put out the 2 to 3 year aggressive analysis out there. I frankly believe that what's happening around the world will have an immense impact on the cost of energy, especially what's taking place in the Middle East. And I wouldn't be surprised if folks will be aggressively pursuing PV options outside of feed-in tariff or other incentive structures just to offset some of their peak requirements because conventional energy sources will be so expensive and so difficult to come by.
Thanks.
Okay, well, I think we'll close it off here. I'd like to thank Todd and Matt and Oleg for their great presentations. Thank you as an audience. You were great, some excellent questions. I know from my perspective, it's been a very enjoyable last hour and a half. As I said earlier, we are committed to continuous improvement of the feed-in tariff program at the Ontario Power Authority, and this informal stakeholdering to me has been very beneficial. So thank you all, and thank all of you. Thanks for attending, and I'll pass it on to JoAnne.
I also want to thank you, JoAnne, for moderating the session. And the insights were extremely valuable when there's that many questions coming from the audience. Thanks very much, everyone. Oleg, really appreciated you sharing some of your monitoring and maintenance and performance information. And Matt, here at MaRS, we can very much relate to the burden of proof that entrepreneurs face in power electronics and other industries. And clearly, Todd brought up a lot of issues. There's a lot more discussion that needs to go on And the innovation side of this is, energy storage, smart grid technologies. Everything needs to work together to get us there. Really appreciated the insights. And I encourage everyone to stick around, continue to talk. There are a lot of bright minds in this room that can work on these problems further. And with these problems comes tremendous opportunity as well. Thanks very much, everyone. One last thing, I also want to thank the Canadian Solar Industry Association, Ontario Sustainable Energy Association, Canadian Electricity Association, the NSERC Photovoltaic Innovation Network, and Young Professionals in Energy. All of them helped us advertise this event and reach all of you. And also wanted to mention that the Courtright trailer is out in front of the MaRS facility, where they are showing the various components that go into a rooftop solar system. So I encourage people to both stick around and chat and also visit that. Thanks.